How you guys doing today? Great, glad to hear it. So, good. All right, so we are going to be talking about gradient descent today. We will probably be talking about gradient descent and PDEs. I hope that it won't be exclusively gradient descent, but we may be. Now, it should be the first half we'll be talking about gradient descent, the second half will be will give the first introduction to the heat equation and to partial differential equations. But before we get started, are there any questions? Okay, so let's get started. And can everyone hear me all right? Just to make sure. Cool. So today we're going to be talking about fitting ODEs with gradient descent. And then in the second half, we should be talking about a first introduction to heat, to P. Okay, so out of curiosity, how many people there's only we're missing a couple of people from the call, but how many of you have done some machine learning, inferential statistics, gradient descent before? Okay, yeah. All right, Anjali and Sai. Yeah, so this will be a little bit of review, but one of the things that we'll see here for you guys, I mean, in some sense, this will be a review a little bit because most people do this in calculus. It's just you don't use it. The big difference with computing with doing gradient descent for ODEs and PDEs, and this is what we'll see, and this is the thing that you have to keep in mind, is that we don't have an explicit definition for the function. And as a result, we can't compute the gradient. That's what makes it hard. So we will take a tour through the mathematics of this before we actually start implementing it. And then we'll look at some of the pitfalls. Because unlike a lot of other machine learning where, in a lot of machine learning models, you're essentially using things that are almost linear models, right? If they're not linear models, they're very, very close. Even, fairly complicated things like convolutional neural networks almost linear models. They're sort of linear models post-composed with some smoothing, right? PDEs are decidedly nonlinear, and we'll see that that causes a lot of problems, or potentially causes a lot of problems. Okay, so the way that we're going to be fitting and where gradient descent falls in is in roughly the loss minimization framework. But I'll have to trust both of you to ask me the hard questions on this. So the idea behind the loss minimization framework is that we're going to define, so given some data, so data points, oh, sorry, we're gonna be in the world of T here, so let me, so Ti, and I'm gonna stick with Yi though. Ti Yi for I equals 1 up to n. So something like our SIR data. So here. This, of course, is a point Ti, Yi, and down here we're going to have our T1, T2, up to Tn. I am going to assume that the T's are ordered. That is not an assumption that we need to make, but we don't need to assume that they're evenly spaced or anything like that. Okay, so then we're going to propose a model. And specifically, so we're going to propose a functional model here. And in this case, the functional model that we propose is going to be something like the SIR model, right? So S prime is equal to minus beta S I, and I prime is equal to beta Si minus gamma I. So in particular, this gives functions so S, which depend on T, and also depend on beta and gamma, and I, which depends, of course, on T, but also depends on beta and gamma. It's pretty common, I'm sort of stealing this from the probability literature, but it's reasonably common to separate your variables out from your parameters with a line. Okay, so of course, so this gives us some nice model. This model, of course, depends on the parameters beta and gamma. And we want to evaluate how good of a job we did. So for some beta gamma, we want to evaluate our model. How close our model is to the data. So the usual way that we do this, or one way that we do this, is by defining an error. So an error basically is going to be the degree of difference between the data and the model. So some measure of difference between the data and the model. So usually this is done pointwise. So for instance, the simplest error, the error that you're all familiar with is, well, we look at what the model predicts, right? We look at the difference. So this point here, for instance, is going to be Ti I of Ti, right? And we make some evaluation of how far off our prediction is. So the difference between the data and the model. So examples of such errors, say, common errors. So the most common error by far is the mean squared error. So what is that? That is mean squared error. This way. I'll write it out for this model. So the mean squared error of beta and gamma, right, it's going to depend on two parameters, is going to be the sum over all of our data points sorry, 1 over n for the mean, of the actual value, so yi, minus the predicted value, squared. Okay. So any questions about this? So this is a formula that probably most people have seen before. So how do we determine the error of something? Well, we look at the squared error. This isn't the only error function that we have to look at, though. So other examples include the absolute or the mean absolute error. So this, instead of squaring, we just take the absolute value. So mathematically, if we were to take the square root of this, this would be the L2 and this would be the L1 errors. There's a whole family of things, of course. So RSS is the version of this where you don't divide by n, etc. There's all these sort of families of different errors that are basically equivalent to each other. But mean squared error and mean absolute error are probably the most common. And of course, they're going to behave a little bit differently, right? So mean squared error oh, okay. So if this is the error, then our goal, so let me see what our goal is before I start. Find beta and gamma to minimize the error. To minimize the chosen error. Great. So that's our goal. And our choice of metric, or our choice of error function or loss function. So this error, I should say, errors or loss functions. Oops. So your common errors or loss functions will depend on what fit you get. You are making a substantive choice when you choose your loss function. And as a quick example here, we can actually look at the mean squared error and the mean absolute error and think a little bit about, so if we minimize the mean squared error, right? The mean squared error grows very, very fast as the difference becomes large, right? This is the squared term. So essentially, if you double the distance between two terms in the mean absolute error, it will roughly go up linearly, right? If you have, so if you double the distance, it will be the same as adding another, if you double the distance, it'll roughly go up linearly. Whereas if you double the distance in the mean squared error, you'll go up quadratically. So in particular, the mean squared error is going to heavily, heavily punish points that are far away. It'll heavily punish outliers compared to the mean absolute error. Okay, so this may be an advantage or a disadvantage depending on what you're trying to do. There are plenty of cases where punishing outliers is actually not that helpful, depending on sort of how you expect your data to be structured. So it's a call. There are other reasons to use the mean squared error, and there is another optimization framework that I just want to mention really fast. And these frameworks are sort of in tandem to each other, but in some sense, one of the reasons that we use the mean squared error is that both of these are making a call about how we think the noise is distributed, right? What the best way to fit the noise given some assumption about the underlying distribution. And in the case of the mean squared error, basically what we're assuming is that the noise is Gaussian. So that's why we tend to use it, because in the background for the mean squared error, by using the squared term, you can see that it's sort of equivalent, well, it's equivalent to doing maximum likelihood of Gaussian noise. And let me just stick on, okay, so are there any questions about this loss minimization framework? So the idea here is that we have some data points. We propose a model. The model depends on some parameters. And now we're going to try to fiddle around those parameters to minimize some pointwise loss function, or some loss function. Is there interest in me saying a quick word about maximum likelihood? I can at least define it, or we can push that off to applied statistics. Okay, yeah, I'll say a quick word about it. It is useful to know about because it is kind of the other framework. So loss minimization, we start with the idea that we have a functional model, right? So we've got some noise and we've got a function. So let me just at least say this so that you know what the words are here. Okay, so maximum likelihood framework. So the idea behind maximum likelihood is, again, we have some data. Again, we have data, ti, yi, I equals 1 up to n. And instead of now proposing a functional model, we're going to propose a probabilistic model. A probabilistic model. So the simple example is just a functional model plus a prescribed probability distribution for noise. Probabilistic model. So let me say what I mean by that. Sorry. So given any t, we're going to propose a probability distribution So probability distribution on y at ti. So this is called the probability of y given t. And so this thing's an honest God probability distribution, integrates to 1 everything else. So here we have our t, here we have our y. We have some data points. And so what we're sort of saying is, so at any, our model now is going to be like a little bit more complicated. So not only do we have, say, I'll just get a sort of a simple functional version of this in a second. But so not only do we have, so we don't really have this line. Really what we have is at each point, we actually have like a little probability distribution, right? So for ti, we have like a little Gaussian distribution. Actually, that's probably a better way to draw it. We have a little Gaussian distribution around. So like for instance, this may be our mean. We actually have where along each slice here, this is a Gaussian distribution. So like, what would we want to say? So then the probability of y given, so the probability of y given t is something like the normal distribution centered at I of t. Sorry. Normal distribution on y with mean I of t and sigma sigma. So we will have to fit sigma. We'll have to fit the standard deviation. Okay, so there's nothing like, in some sense, that different here, right? I mean, of course, we can make this all very like much more general, but in some sense, there isn't anything that difficult so far. It's just that in this case, we didn't actually stipulate what the noise looks like. And in this case, we are stipulating what the noise looks like. In this case as well, the expectation value is going to be this functional model. But if we were to think about like sampling this thing, right, then we would just go to each point along our model and we would take a sample. And so, for instance, sampling it, we may get another set of data points, and they would be noisy as well. And hopefully the noise would be distributed roughly as the underlying noise actually is. But it's sort of, in some sense, it's a bit more of a correct model because all of our assumptions are out in the open, right? We are making a claim about our functional model. We're also making a claim about what the noise looks like. Okay. Well, I shouldn't maybe say it's more correct, but I don't know. It's more like it's more complete, right? Okay. Any questions about the setup anyway? Let me just say how you say this in case you. So this is probability of y given t. Okay, so then the question or the goal is to figure out how likely it is that the data points were actually drawn from this distribution. Quantify the likelihood the data was actually drawn from P, right? Because of course we could just propose some crazy model and, that has nothing to do with anything we see here. So this is going to be our fitting. I'm sorry, I should say our eventual goal is our goal right now is to quantify it, but I'm just going to say it in a second. The actual goal here is to maximize the likelihood. Okay. So the likelihood in this case is fairly straightforward. The likelihood is just, we're just going to use the probability density function. So the likelihood that a single data point was drawn from this distribution, so this is Ti, Yi, came from P, is just given by the density function. So this is just the probability of Ti serve Yi given Ti. Okay. So in our example, what is that going to be? Well, okay, I don't remember. There's a bunch of coefficients outside the normal thing. So this is going to be P of Yi given Ti. Well, this is a normal distribution, so it's going to be 1 square root of 2 pi sigma squared times bxp. So this is just your standard Gaussian normal distribution of the difference between the data point and the mean, great, which is yi minus I of ti squared over 2 sigma squared, okay? And again, so this is just the formula for the bell curve, right? If you haven't seen, this is just your standard formula for your standard bell curve. So this is the probability, or this is the likelihood of drawing a single point. So if you're far out in the bell curve, the likelihood's lower. If you're closer, the likelihood's higher. The total likelihood then so this is now some L that depends on beta and gamma. Or of course, I'm just using beta and gamma because I'm assuming the SIR models in the background. It really just depends on whatever parameters that you're working with. So it's an L that depends on beta and gamma. Now we're going to take the product of all these things. I equals 1 up to n of 1 over 2 pi sigma squared exp yi and I realize now this is the example, not the so sorry, the total likelihood is just the product of all the likelihoods, right? Because product of likelihoods. So call this Li. By the assumption that the choices are independent. So right, so by the assumption, by the assumption that in the distributional sense, picking the noise doesn't depend, the noise at point T1 does not change the noise at T2. Is independent, right? We're assuming that any dependence between T1 and T2 is packed into this, into the mean. So in our example, we have this. Okay. So now here's the thing to notice. If we want to maximize this, we actually, oh, and I've made a huge mistake here. I apologize. There's another parameter in here. Since sigma is clearly a parameter. Yeah, sigma, great. So if we want to maximize the likelihood, we can pick sigma just based on finding the standard deviation of the difference of the residuals. Want to maximize, so fix sigma by finding the STD of just these terms, yi minus I of ti. And then what we're left with is the fact that, oh, sorry, I've made another huge mistake. It's a Gaussian function, so we must have. Okay. Okay, so if we're trying to maximize this, right? Since this is e to the something squared and negative, so this is always going to be positive. So the way to maximize this is to maximize the individual terms, which means that we need to actually minimize the distance between yi and I squared, right? So we do this, so we fix this, then L of beta gamma sigma is equal to one over 2 pi sigma squared to the n. What happens when we take the product of a bunch of stuff? In the exponent, it becomes a sum, minus the sum from I equals 1 to n of yi minus I of t squared over 2 sigma squared. So look, lo and behold, 2 sigma squared is constant. So maximizing the likelihood is the equivalent to minimizing the mean squared error. So, maximizing the likelihood when we have Gaussian noise. Okay. So this is something that's really kind of nice to know about or to be aware of, because what it's telling us is that secretly what we're doing when we're minimizing the mean squared error is that we're maximizing the likelihood, is that we're making some assumption on the noise in the model. We're just saying, okay, we're secretly assuming the noise is Gaussian. You can make similar determinations for the mean absolute error. So there's, if you assume the mean absolute error, then you're thinking about another distribution, etc. However, both of these forms are also useful sort of in their own right. So it's also good to just remember that they're both floating out there, especially if you get more into the world of optimization and sort of mathematical machine learning. Because there can be problems that are very easy to solve in one form that are difficult, or maybe not easy to solve, but where there are nice tricks when you look at it in one form, and when you look at the other form, those tricks don't seem to exist. But that's basically the idea, right? So we've got two frameworks, maximum likelihood and loss minimization. And they are, in essence, they're both kind of doing the same things. One is a probabilistic framework and one is a more functional framework. But at the end of the day, there's like a strong equivalence between the two of them. Any questions? Okay. So how do we actually minimize? But this is here as this side. Okay, so how do we actually minimize things? So there's a handful of ways, just to mention them. So one, we do a grid search of parameters. So what do? Well, we look at gamma, beta, cut them up into a grid. This is some gamma I beta I. And we just check for every element on the grid, right? Oh, sorry, gamma I beta J. So check the mean squared error for we find the minimum. Okay. So there's actually, I mean, there's in principle nothing wrong with this, but what could go wrong? Why might we not want to use this method? I do want to mention this method because you should definitely keep it in mind. It's not, you know, it's a perfectly reasonable thing to do. But why might we not want to use it? Yeah, so these are both great reasons. The grid size might be, you know, we may just not, you know, okay, like what if the minimum's here and, you know, but these are all, you know, large or something like that. So the grid, we may miss it. So grid size may affect results. Yeah, so by oscillate, Annalie, do you mean, so another thing that could happen is you could just have some repeating behavior, right? And it might be, you know, you might wind up in a case where, for instance, you know, if you had something like sine or something like that, you're just sort of randomly saying, oh yeah, the minimum's right here, when in fact the minimum's periodic, and you just can't see that behavior. Hard behavior. Sorry, I want to say affect results, may miss points, right? Any other ideas? These are both solid issues. There's a couple of other big ones though. Or I should say there's one other big one. Maybe two other big ones. There's a lot of big ones actually. So one of the big one is it's just really computationally expensive. So in particular, if you have like p parameters, for B with B values, right? What's the size of this going to be? Well, it's going to be, or if you had V1, V2, V3, whatever, you could do this as well. It's going to be O of V to the P. So it's just really computationally expensive. And furthermore, most of those values may be in completely uninteresting regions of space. Right, like if you have some nice, minimum that looks like, everything's flat, and then you just have like a nice minimum in some part of space, this doesn't see that, right? It just continues to waste time wandering around in flat regions. Okay, so I should say, so all these can be fixed. So grid search. So lots of improvements. So for instance, you could have a shrinking, zooming, targeting. So zooming. You can have a log-based grid search, right? Where instead of doing some sort of uniform thing, you do a log thing to set your variables. You can do stochastic. So this is actually very useful. So instead of doing a grid search, you just put a probability distribution in all of your parameters and you sample it many, many times. But in general, it's actually quite useful. Can be useful. And as another one, it works for non-smooth functions. Works for non-differentiable functions. So don't discount grid search out of hand. I mean, especially as like a first, if you're fixing one variable and you've got a reasonable idea of where it is, just do a grid search. It's fine. But I do want to mention, because this is one of the main ways things are done. The second is gradient descent. So gradient descent is the tool that is used most often probably in modern kind of machine learning optimization, at least at some level. So I should say that there's actually sorry, I should put one more in. Nah, actually I won't. Okay. So there's also, so the most common actually is linear programming. That may be changing with the prevalence of neural networks, but linear programming is a really, really powerful framework for optimization, but it requires putting things in terms of a linear program, which is more complicated. But that's fine. If you take optimization and complexity, you'll learn about linear programming. It's by far the most efficient and powerful framework, and I think it's probably still the most powerful or the most used optimization that sort of is out there in the ether. But gradient descent, but it involves being able to cast your problem in a very specific way. So gradient descent is much more general. And the idea is the following. Assume we want to minimize some function. Say f of x, y is x squared plus y squared. So this is our sort of, this is our kind of standard Calc 3 function that we spend huge amounts of time on. X, Y, Z, right? This is Z equals f of x, y. So recall the following. So we have some point x, y. So I'm just going to assume that I will happily prove this fact here, but just in case, recall the gradient of f at x, y points in the direction of greatest increase of f. So for example, the gradient of f in this case is just 2x. Sorry, let me do my example in different colors so it's clear. Gradient of f is 2x, 2y. So for example, the gradient at say 1, 1 is 2, 2, right? At minus 1, 1 is minus 2, 2, etc. And we can go around and we can see that we're always, if we go up and project up, we're always pointing in the direction of greatest increase. Okay, any questions? Or maybe I should say, so first, any questions? Second, is this a fact that everyone remembers, that the gradient points in the direction of greatest increase for a function? I can happily prove it again if you want. It's a two-line computation. Okay, so if the gradient always points in the direction of greatest increase, then that means that if we want to find a minimum, we can just walk the other direction. Sorry, say walk the opposite direction. Minus delta f. So in that case, this is minus grad f. And what we'll do so if we have our y equals x minus 2 squared, the gradient, sorry, is equal to f. Gradient of f is minus 2, x minus 2, minus the gradient is 2x minus 2. And so what's that telling us? That tells us that when we're at 1, we should go in the positive direction. And when we're at 3, we should go in the negative direction. And eventually, what do? We sort of bounce down, hopefully into the minimum. Okay. So, any questions? All right, so the algorithm then is pretty straightforward. So if we want to extremize, or if we want to find a local minimum, to find a local minimum, what are we going to do? So for f of x, sorry, vector hats aren't working very well. To find a local minimum for f of x, what are we going to do? Well, we're going to pick some initial starting location, compute the gradient, and then we're going to move a bit in that direction. So to formalize all that, fix start location x naught, and then we're going to fix what's called the learning rate, or the step size. Or learning rate. We'll call that lambda. Then here's what we do. Sorry. xn, so the next step. So given some starting point, we're going to take a step in the direction of the gradient. So xn is going to be equal to x n minus 1 minus lambda delta f of x. Sorry. N minus 1. So what do? So at our point, we compute the gradient, we take a step in the direction of the gradient, and then we scale that by our learning rate lambda. So one of the nice things about this, right, is that the gradient, if the function is steep, which we sort of assume would mean that we're farther away from a minimum, then the gradient will be larger, so we'll take a larger step. Whereas if we're actually close to the minimum, then the gradient will be smaller, and so we'll take a smaller step naturally. And what we usually do is we usually stop when the length of the gradient is less than epsilon for some fixed epsilon. Okay. So are there any questions? Okay, so now we're going to shift our thinking over to loss functions, and this is this can be a little bit challenging. It is, you know, there are these occasional things in mathematics where the first time I'm going to say it and you're going to see it, and then we will need to discuss it. You may need to take it. You may need to think about it a few times before it really solidifies in your head. So how does this apply to loss functions? Okay. So let's look at an example of a linear model. So the big switch that's going to happen here, just to tell you, is that this entire time we've been thinking about these variables as being sort of the things that change and the parameters as being fixed. And we're going to do something different. What we're going to do here is we're actually going to fix, the data is going to fix the variables now. So the variables will be completely fixed and will no longer be dynamic. And the parameters are going to become the things that change. So in everything that follows, and I'll write this down explicitly, what we'll be seeing is that the variables, what were the variables before, are actually no longer variable. They're actually completely fixed. It is the parameters that we're going to be doing all of our optimization on. So let's say we have some data points, and we've got some model. Stay x plus b. And our loss is going to be mean squared error. So mean squared error now depends on two variables, sorry, two parameters, a and b. And it is equal to the sum from I equals 1 up to n times 1 over n times the sum from I equals 1 up to n of, again, so this is going to be t, oh, sorry. Yeah, let's keep everything t just for convenience. T and y. So this is going to be the sum of yi minus a ti minus b, right? So this, of course, is our guess for each y squared. So this here is f of ti. And so what we want to do now is we want to optimize the mean squared error with respect to a and b. Okay. So what that means is that we need to compute the gradient of the mean squared error, which now is going to be the partial derivative with respect to A and the partial derivative with respect to B, right? And we can go through and do this. It's not super hard, right? I don't know how instructive it is, but just to see what this kind of computation looks like, maybe. Okay, so just to see a quick example, right? So what is the partial derivative of this going to be? We can certainly do it inside of sum. It's not that hard. It's just going to be 1 over n times sum from I equals 1 up to n times minus ti, partial derivative with respect to a, yi minus ati minus b. Oh, sorry, factor of 2 is going to come out. And similarly, with respect to b, it's going to be 2 over n times the sum from I equals 1 up to n of minus sign is going to come out. Otherwise, it's just going to be yi ai ti minus b. Great. Okay. So again, notice that this no longer depends on t or y. So any questions? And so this is the shift. The shift here is that if we want to minimize the mean squared error, what we do is we write it down with all of our data in it, right? Then we get some concrete function, right? Y is 4 and T is 7. There's nothing mysterious, there's nothing, the only variables that are appearing here are A and B at this point. And so then we optimize. So then AN BN is equal to AN minus 1. Sorry. I'm going to keep my calc 3 vector notation. BN minus 1 minus lambda times delta of the mean squared error. At AN minus 1, BN minus 1. Okay. So let's recall what we did really fast. So we said, so given some data and given a model, we define a loss function. The loss function is roughly just going to be the difference between the two. Now we're going to try to minimize that. We could minimize it by using grid search, right? We could just, we could just take this loss function and just plug in a bunch of values of A and B and take the best one, right? There's nothing wrong with that. But we can also use a slightly more sophisticated method, which is gradient descent. And gradient descent is going to then, and gradient descent has the advantage that it will, instead of doing this big random grid search, we start it off at a point and it will just walk towards a minimum. Now, there's problems with gradient descent. It may walk towards a local minimum instead of a global minimum. But what can you do? It at least finds you something. And this is the general schema, right? So if you have a model that's based on n parameters, you just plug it in, you compute this gradient by hand, usually. You don't, compute this gradient by hand, and then you just update it over and over and over and over and over again. And this is, yeah, this is what everything's doing. This is what neural networks are doing, just on a much more sophisticated level. Okay. So now we're going to fall into the final piece, gradient descent for differential equations. Sorry, I should say for ODEs because okay, so the reason, let me just say why we need a special topic here at all. So the reason, right, is that everything that I've done so far, we have an explicit function for f. Of course, what we've seen with ODEs is that for even some very, very simple examples that we can write down, like the SIR example, we cannot solve them for an explicit closed form solution. So we have an explicitly defined model. Like f of x equals x squared, something like that, right? Some explicitly defined thing. For most ODEs, we don't. There are some kind of sophisticated ways, well, okay, let's say, for example, our simple SIR model, there isn't an expression for S and I. Okay. So what do we do? Okay, so a sophisticated answer is that you can look at these derivatives because if you think about it, this whole gradient descent thing actually doesn't depend on the value of the function itself. It only depends on the gradient. So you could try to think if you could maybe try to do something here, but the problem, of course, is that these are derivatives in terms of S and I, not in terms of beta and gamma, which is what we need. So there are some sort of sophisticated solutions where you can kind of try to integrate around that a little bit. But in general, we can just estimate the gradient. So we've got to estimate the gradient using ODE-end. Okay. So how do we do that? Well, we'll say something like di d beta is going to be approximated anyway by I of beta plus delta beta gamma. minus oh, sorry. I don't want I here. This is sorry, be a little more careful. This loss function, right, is going to be estimated by making a small shift. So this is our numerical estimate. And so we can use this, so we can estimate delta L. And furthermore, we actually know one nice thing, which is that these ODEs should be smooth, right? So we should actually be able to make this estimate pretty good. Okay. So any questions? All right, so I know I've hit you guys with a lot of optimization in one quick go, but this is the plan. Here's the plan. We write down our model. So given a system of equations, given data ti, yi, so we write a model using ODE int. Use ODE int sorry. Let me be a little more clear. So given some data and a model, we want to pick some starting parameters. Model. So given this and a model, so we pick starting parameters, and of course, so these are going to have to include our initial conditions as well, right? Those are parameters. So pick starting parameters, beta nod, gamma nod, I nod, S nod. And then, so what do we do? So given these parameters, we compute, given some vector, beta n, gamma n, I n, S n, we compute the solution numerically. using ODE-int or whatever other numerical solver you could possibly want. So get a numerical solution using ODE-int. And then we're going to use that numerical solution to compute the loss function. Then we're going to repeat for slight shifts in each of the variables. Use those slight shifts to estimate the gradient of the loss function, and then use gradient descent. So beta n plus 1, etc. is beta n minus delta L. Okay. So this looks complicated, but like, oops. If I asked you to go off and do it explicitly on a homework assignment, you could totally do it, right? There's nothing, you know, it would take a little bit of work to figure out the moving pieces, but there's nothing like super mysterious about it. The nice thing is that this will be, Python will do this for us automatically. Specifically, SciPy will do this for us automatically. So let's take our break, and when we come back, I'm going to show you guys how to implement this. And as before, so I apologize. I'm just going to do the code. I can upload. Yeah, I'm just going to do the coding, and then I will upload the file afterwards. It's not sort of as robust as a lab, but we'll do a couple of examples, and we'll see some of the pitfalls as well. So we'll see some of where it can be incredibly useful, and we'll see where some problems are. So it is 2:21 now. I will start up again at 2:31. And yeah, if you have any questions in the meantime, please let me know, and I will do my best to answer them. Yeah, let me grab some coffee really fast. Use numerical solutions to compute loss basically means find. Yes, exactly. Yeah. So we find the mean squared error, and then so actually we could kind of combine these two steps into one here, right? Because essentially we find the mean squared error for, in this case, it'll be 5 cases. So the mean squared error when we adjust beta a little bit, when we adjust gamma a little bit, when we adjust I and S a little bit. And then using all those, then we compute these derivatives. But yes, you're absolutely correct. Any other questions? Oh yeah, I also want to say, so this, what I'm going to show you, or this methodology of wiggling the function a little bit on the parameters and estimating the gradient that way, you don't have to use that for just differential equations, right? Basically, anytime you don't know the derivative, you can do this, right? This is just taking some sort of basic first-order numerical estimate of the gradient. It's a perfectly reasonable thing to do. it's going to be as sensitive as your shift in parameters is. So, I mean, you can even do this on non-smooth things if you want. It's just possible that you'll get wacky results. If you're interested in that, optimization or complexity or machine learning would be, we talk a little bit more about what you can do and what kinds of wacky results you can get. But we'll see an example here in just a second. All right. Get to this. Fire it up. Are there any questions before we get started on the coding portion here? Okay, so let's just remember what our plan was. Right, so our plan was that we were going to so is this big enough that everyone can see? Is it too big? Not gonna do that at all. Okay, so is this big enough? Sorry, is this big enough so that everyone can see the code here? And again, I'll upload it shortly. Cool. Okay. So we're going to look at this SIR model again, and what we're going to use is come on, get that really fast. We're going to use this least squares optimizer. So this least squares optimizer in the SciPy toolkit it's just a very general optimizer that does exactly that thing that I talked about, where you feed it a model, it makes a little parameter shift, and then evaluates the gradient using that little parameter shift. So, okay, we know what this data looks like. This is our boarding school SIR model. And so our steps before we were going to define the model. Then we're going to define the loss function. We're going to give our initial conditions on the parameters. And then we're finally going to optimize. Okay. So define the model is going to be exactly the same as before. So the model is going to take, this is going to be a ODE int model, right? ODE int is going to be the thing that does our integration for us. And so we're going to feed it in some parameters. I'm going to say beta, I'll just use BG equals P, and then return, we can just do it in one line. SI equals Y, B times S times I, B times S times I minus G times I. Great. Okay, so that's our model. So now we're going to define our loss function. And our loss function now needs to only take one thing. It needs to only take the parameters. So in this initial example, I'm going to do something which you can do in Python, which is sort of abuse global variables. And I'm just going to leave this stuff written out here and define the loss. Now, this is, I should say, define, actually, error. I want the error rather than the loss, because actually what I want to return is the differences in our model and the parameter values. So optimize least squares will then square each one of those and do that and sum them up for us. Okay, so we need to compute our model. So take our usual solution equals ODE int model ynod t. Oh, make sure that I'm getting that in the right order. Yes. Okay. And then we're just going to feed it one. So P is just going to be our list of parameters here, right? And then we're going to return. All right. So we only have data for the infected. So that is the only thing we're going to be trying to fit here. And so instead of instead of returning the solution, right, we're just going to return the part of the solution which is the infected data, which is the second column, right? So the first is the susceptible, the second is the infected, and we want the difference between that and the actual infected. And so we should get that, and we can test this really fast. Let's just check error, and we'll feed it in some initial p-values. I don't know, 0.1, 0.1. And here we go. So we get the errors in each estimate. Okay, so any questions so far? So the model's the same. The error we're getting exactly the same way as we said, right? We use ODE int to generate the model, and then we just take the difference between the actual parameter values and the predicted parameter values. And now we just need to use the optimizer. So we'll give it some initial parameter values. I don't know, 0.1, 0.1. Let's let it, define loss. And there it goes. And it runs something. Let's actually do 0.01. There we go. Okay. And if you may actually remember from our lecture on Monday that this is actually pretty close to, so 0.44 is actually what we were using for the the recovery rate, and 0.002 is actually pretty close to what we guessed. You'll notice, so what this returns here is this returns a tuple, right? And it returns a tuple with two things in it, an array with our parameter values, and then this integer. And what this integer is this integer basically tells us whether it was successful or not. So this allows us to check whether or not the optimization algorithm thinks that it actually found a minimum. So 1, 2, 3, 4 means it was successful on some level. And each of those flags means something different, but in general means it was successful. And if you don't get a 1, 2, 3, or 4, then that means it was not successful. So we do have to do a little bit of work to actually extract these parameter values. So for instance, we do 0, then we get the array, great. And so what we need to do now is, so if we want to plot this, so we'll plot our infected, and then we want to actually take these parameter values, feed them back in, and see how we did. So ODE int model, use our initial conditions again, T, and then we just need to feed it our parameters, which is going to be, just remind ourselves how to extract those, opt 0. This is still going to be, and there we go. So not bad. Okay. So are there any questions? I'll go through that again, just to explain exactly what we did. But first, let's stare at this plot for a second, and let me just slow down and ask if there's any questions. Yeah, so what does the 1 indicate in the array? So the 1 is actually a flag that least squares is returning. And basically what it's going to indicate for us is whether or not the function least squares thinks that its optimization was successful. So there's a couple of different flags, and if you want to look them up in least squares, you can. But basically 1, 2, 3, or 4 means that it thinks that it was successful, and 0 means that it doesn't. It means that it searched around for a while and then just reached a fail state and said, I couldn't find a minimum. So basically, it's a good way to check if you want to automate this. You can always just check and see, hey, did it actually succeed or not? Any other questions? If you want, just for the fun of it, we can actually throw in a little print statement here. And let's print the parameters. That's a good thing to see. So let's just actually watch what happens to the parameters. So we're starting out at 0.01, 0.1. Let's actually just watch what happens to the parameters as we fit here. Okay. So it feeds these in a bunch of times, right? So how many times does it feed it in? Well, here it's computing the derivatives. Then it makes an update, makes another 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 update, and feels like it's settled down. It has reached below its error threshold and returns these final values. Okay. Cool. Any questions? All right, so this is great, right? What is pat.plot infected? Oh, this is just a, yeah, so basically, so infected here is just this list of the values, and T is the list of times. And so this is just plotting these dots on here. And then the O just indicates that it should be a scatter plot, not a line plot. Any other questions? Okay, so I want to look at a slightly more sophisticated example. Oh, actually, well, let's look at one more example. So what happens if we fit the initial population as well, right? So the initial population is a parameter. We can totally fit it. And let's just take our code and do that. So I'll take this print statement out. And so I want to, yeah, again, so I'm going a little quickly here, but if you want me to slow down, do just ask. I'm more than happy to, or repeat anything. So I'll grab these plots out. Now print. And okay, so if we want it to fit the initial parameters as well, that just means that we're now going to have 4 parameters instead of 2. So let's call these 7, 6, 2, and 1. So we'll make just the first two are going to be the initial value, and then the second two are the parameters that we're going to fit. So the first thing we have to do here, so ODE, and we need to feed it y0, and we need to feed it p. So we can just tell it, well, y0 is going to be, we have params. Let's call this params now as well. Params. We want the first two to be the initial conditions. And then we want the next two to be the parameters. And so now it'll fit the initial condition as well, right? The initial condition is something we specify. So let's see what happens. Oh, okay. Well, something's, oh yeah, I need to fix this. Sorry. So now this needs to be 2 on, and this is condition. Whoa. Okay. So something seems to have gone horribly wrong here. And we could worry that it's the code, but I'll just tell you right now it's not. So what has gone horribly wrong here is that we've fallen into a local minimum, right? So again, we have some least squares function, and in our quadratic function, of course, there's only one minimum defined. But for some general function, there can be all kinds of local minima all over the place. And it's very, very easy to fall into one without, to fall into a local minimum that is actually quite bad and is actually quite far from the global minimum. And this is in particular a huge problem with fitting differential equations, just because you've got all of this numerical impreciseness, you've got quite complicated functions. And so you do have to be very careful not to fall into a local minimum. And fallen into a local minimum. And so the reminder here is just that it can be important to use any information you have to restrict the parameter space. So that does not necessarily mean that we shouldn't fit the initial conditions for every problem. We'll actually, in just a second, we'll see an example where we really should fit the initial conditions as well, because the information is noisy, right? In this case, the initial conditions, we want to keep them set because it's actually one of the few pieces of information we really know concretely, right? At the beginning, there are 762 susceptible students and 1 infected student. If that is a fact of the matter, then we want to hard code that in and not fit it. But this is a first example of how things can go wrong. And it's one of the reasons that, this entire semester I've been kind of hedging and talking about these a priori, not a priori, but well, let's think about this carefully. Let's think about, we're fitting oscillating solutions. Can we do something like, fit the period, or look at these kinds of estimates when, gamma, or when one of the functions is small and things like that. And the reason is because it's very, very easy to get bad fits when you're fitting differential equations. It's a big problem. And it's an interesting problem right now. That's kind of that there's a lot of work being done on still. How do you fit parameters to interesting ODEs and PDEs? Okay. Any questions about this example before I move on to the next one? Okay. So let's look at a competition model here. And I'm stealing this from this great website. Oh, sorry, still confused. Why was it returning a beta and gamma value in the array? So here, let me take this, sorry, let me take this print statement off really fast. So the reason, right, is, let's recall our whole setup here, right? Our whole setup is that the optimization function, in some sense, you feed it a beta and gamma value, right? And then, sorry, our error function, right? You feed it a beta and gamma value, and then we do all this computation, we compute a loss, and then we return for it a least squares estimate of the loss, which is just a number, right? In fact, we return a list, and then it computes the number for us. But at the end of the day, you give me a beta and gamma value, and I give you a number back. And that's a function, right? It's a function from beta and gamma to the real line. And so that function is actually the thing that we're trying to optimize, right? The loss function at this point does not know anything about the susceptible or the infected or anything else, right? Or sorry, that's not true. It only knows about that through the data. Yeah, I'm glad you asked again though, because this is, I mean, this is very hard to keep track of, and it's hard to keep track of for me. You know, you just kind of like, wait a second, what are our variables again, and what are our things that we fixed again, and like, you know. And so it's always good to just be clear on what we're actually optimizing over. It's pretty non-trivial. And then there's even another level of abstraction we can go higher to when we do machine learning. Okay. Any other questions? Okay. Oh, and Anjali, for your previous question, you can see that we've hit a 5 here, right? So when we did this, it is returning a 5, which basically means that it knows that something's gone wrong. So in this case, it reached the maximum number of iterations without doing well. So it basically knows it tried to improve. It kept on stepping in the direction of the gradient, but essentially it was stepping too far probably. And so this 5 is indicating, well, here's what I got, but the function knows that it's wrong because this is actually worse than the initial parameter value. Okay. All right. So let's look at a basic competition model. So this is a competition model of some yeasts. And here we go. So you take 2 yeasts, you put them in the same, I think the same petri dish, you give them some sugar or something to eat, and you watch as they compete for resources. And you can kind of see here, looking at these data points, that yeast A is increasing, and it looks like falling off to a stable equilibrium. And yeast B is increasing and also falling off to a stable equilibrium. We can actually label these guys. A legend. Okay. So we can see that our kefir, I think, I don't know how to pronounce these words, that this is a little bit lower and this one's a little bit higher. And so we want to fit our standard competition model to it. And so I'll write this competition model out while we're staring at what's going to happen here, right? But it is our standard sorry. So this is just going to be our standard competition model, where we have X is logistic. So it's going to be B1 minus D1 times X. And then there's some competition term. And then Y similarly is going to be a logistic model. So we've got B2, D2Y, and then some competition with X. we write down our model, and then we define our loss function. And again, I'm going to call this the error because, again, we're not actually returning the loss. The loss is going to be, we take all the errors, we sum them, we square them, blah, blah, blah. And so this is going to be done for us. In this case, though, I want to be just a little bit careful, right? So this is going to depend on params again. And so we're going to have our solution equals ODE, I'll call it Y. So that's really what it is. Well, yeah. So, sorry, Y equals ODE int of model, Y nod T, feed it P. Okay, but so before, if you remember, we had we just had a single, we had the infected, and so we were only comparing sort of one set of values against one set of values, right? Here we actually want to compare, we're going to wind up with two functions, and we want to compare the two functions against each other, right? So there can actually be a question there of how do we want to weight them, right? Do we want to weight them the same? Do we want to weight one stronger? Do we want to make sure we fit one, but we don't care too much about the other? In this case, we just want to weight them the same because we're assuming we're kind of trying to fit both populations. But you can even see here how that could be a bit of a problem, right? If the variance in the lower population is just significantly lower than the variance in the larger population, just because the larger population is a factor of 10 larger, then we could get some weirdness in the weighting. But for now, we're just going to, so now we want to return Y minus these guys. We want to package these guys. Remember, Y is going to be two solutions. We want to package these guys together into one matrix. And the simple way to do that is to use a NumPy array. And so we can stick these guys, I'll do this in two steps. So we can stick these guys, so we have two lists here of values. We can stick these guys together into a list of lists. So as a Python object, a list of lists, you can actually stick anything you want in a list. That doesn't even have to be the same data type. You can stick a word in a list in a list. And then we want to turn it into a NumPy array. There we go. So now this is a little matrix. And let's just check error and make sure that this is working. Because spoiler, it's not going to. Oh, name P is not defined. Okay, so we're getting an error. And I actually want to stop here and just have a quick seminar on how we read Python errors, because Python actually has fairly good error messages, luckily. So this is saying, okay, so we've got an error in, start from the top usually. So we have an error in the function error, okay, right? Inside the function error, the line that's giving us an error is return y minus np blah, 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 blah. And the error actually is the operands could not be broadcast together because the shapes are different. So what this is telling us is that when I created this little NumPy array here, I actually accidentally created it transposed, right? So the y is going to return, so we look at the shape here. This is going to be a 2 by 13 matrix, whereas y is going to return a 13 by 2. So that's fine, we just transpose it. There we go. And that's exactly what we want. All right. Well, it's almost exactly what we want. So there's one final problem, which is the following. The final problem here is that well, this is what we want. That's not what least squares wants. Least squares doesn't know how to deal with a matrix. It wants everything in terms of a just a vector. And that's fine. So there's a couple of ways we can do this. The simplest is to wrap these in parentheses so that it's one Python object, and then we can just reshape it. Well, reshape it -1. And so what that does is that reshapes it so that it just has, it just reshapes it into a vector. Okay, so let's optimize. Go. Okay, so we've got some values. And let's take a look at them. Boom, there we go. Okay. Any questions so far? All right. So I've got a question for you now. Something has gone terribly wrong. It is on this screen. You can see it. And my hint is that we as sort of people with some math background who've been studying this and have been doing modeling for the entire semester and have looked at these equations carefully, can definitely see it. But it's definitely one of these places where people can make bad mistakes if they don't actually understand their model. So what is it? What has gone wrong here? I'll give you a hint. It's either something you can see on the graph or something you can see in this array. So on Jolly's question before about what this function is returning should give a hint, or could give a hint. Exactly. So that is exactly correct. We have a negative value here. And that's a huge problem. So there's a potential that it couldn't be. So if this was a competition term, for instance, then maybe it would be okay if one of the values was negative. It would just be saying that it's beneficial competition, not antagonistic competition. But if we go and see and check what is the fifth value in this array, it's D2. That is the death threshold for the second population. So what that means is that we are actually expecting the second population to grow exponentially forever. So that's a problem. That's a huge problem. So that actually means that this fitting, despite how nice it looks down here, right? This is great. This looks glorious. It is clearly like absolutely there's no way that this can be the correct model with these parameters. And we can even check. I think if we take this out to like 200, I haven't checked this yet. Oh, sorry. Oh no, this isn't. Well, sorry. If we take this out, NP lin space to 100, I think we'll start to see some bad behavior. Yeah, there we go. Okay. So what we're seeing here is that this negative value that Anjali pointed out is actually going to result in this model exploding in one of the populations. By 60, we might be able to see it just completely screw everything up. But even by 50, cool. 55? Sorry, I want to see it explode. Yeah, okay, so we can already start seeing it explode there. Okay. So that's bad news. And that's something where it's important to understand the model, because if you don't understand the model, it could be very easy to just look at this graph and see no hint that anything's gone wrong. There is a hint in the graph itself, which you can sort of see if you know these things well enough, which is this little thing here that's going on at the end, right? If these were really settling down to equilibrium solutions, this wouldn't suddenly be jackknifing up at the end. Okay. So what do we do in this situation? And so the solution is, in this case, we can actually, there's an experimental design thing that we can do, is that we can, so if we have our yeast and we're in the lab and we can just throw the yeast in some, in a petri dish with some sugar, we don't need to put them together immediately, right? We can actually throw one, we can measure one set of yeast in one place and another set of yeast in the other place. And in the case of the competition model, that will fix these parameters, right? We can fix B1 and D1 and B2 and D2 without the presence of the other population, right? This is just predicting some logistic growth. So we'll do that in just a second. But are there any questions before we move on? There's another hint that something's gone wrong here, which is you notice that this has returned 5, right? So again, sort of 1 to 4 are good values. 5, again, is an indication that something's gone wrong. And in this case, it's that you see it's, we're again getting this runtime warning where it reached a maximum number of calls to the function without settling down. Okay. So I'm just going to sort of do this. Yeah, I'm just gonna copy and paste the code in. I've got it, sorry, over here. I want to show you another thing that can happen though really fast. So this is a really subtle. Whoa. So this is a really subtle kind of thing that can happen, but there's something a lot less subtle. So let's say, so here, of course, I just picked some initial parameters that were kind of stupid, right? Well, we could say, well, let's pick really good, right? Let's pick some initial parameters that are actually close to what we expect. And so here are some initial parameters that are actually very, very close to the values we expect. And let's see what happens. So we start here, we fit them. Okay, we're getting warnings, this is bad. And now something else terrible has happened, right? Now we're getting this. So how could we possibly be getting something like this? And it returned a warning, but it returned a successful fit. How could this function possibly be seeing this as a successful fit? So this is where I expect anyone who has any machine learning background to jump in with the great problem of machine learning is what we're seeing here. So this is an example of what's called overfitting. And where the problem comes in is that basically, again, the optimizer and the error only see the data points, right? So it only sees this point and this point and this point and this point. Nothing else comes into the computation at all, the computation of the error, right? So if we're trying to optimize, this can be absolutely as bad as it wants to be. This could go off to infinity and back. We're never going to see it. And this is the other big problem with machine learning, is that if you don't have enough data points, if we had a ton of data points, we had this massive forest of data points where we could basically just fill this in, then we could probably fit this quite effectively. But in this case, we don't. And so we have enough parameters in our model that our model can start to just contort itself around and do all sorts of terrible things in the regions that we're not looking at, that we can't evaluate because we don't have any data points there. And this is like the biggest problem when you're trying to use computers to fix parameters. So the two biggest problems, one are finding parameters outside of the actual model domain. And the second is, the second even bigger problem is overfitting. This is especially a huge problem if we're trying to do inference on new data. So if, for instance, we have all of the traffic predictions up to today, and we want to predict something out in the future, then overfitting can be a huge problem. All right. So what we want to do then, what we can do is we can just we can fit the first two parameters using individual, or using little yeast calculations for just the first two. And here, I'll show you how to do that. Well, sorry, I didn't import things correctly. Okay, so here we're just going to use our yeast being grown alone. So I want to make clear, these are different experimental results, right? I have not taken those two pieces of data and separated them. We've gone off and done more experiments, and this is going to allow us to fit things. So, but the model is just simple logistic model, right? Y times B minus dy, great. I do exactly the same thing. The only difference is I'm actually going to let, I'm also going to let this guy fit the starting parameter. Sorry, the starting value. And the reason why is because it's a little noisy, basically. The data is a little bit noisy, and so we actually, it's not like in the case with the school where it's like we actually knew that there's one infected kid, and so there were 762 non-infected kids, and that was that. Here, like we're taking imprecise measurements, and so we want to actually allow the first parameter, so the initial condition, to be fit as well. Get some nice results. Similarly, we can fit our other yeast. We get some reasonable results. We're getting an error message. We should check that, but it's just a warning. So it's okay. And then if we take these, so this initial, if we take these B and D, we're not going to take the initial condition, of course, because these are two different experiments, but we'll take the computed B and D values, plug them back in to our initial equation so that we only have to fit two parameter values now. So we've got B and D fixed. We're going to, yeah, so we've got B and D fixed. We're going to let it pick the initial conditions as well. And here we finally get something reasonable looking. So this is kind of your methodology. So these are the methodologies and the pitfalls of automatic fitting. It's very, very useful. And if you have quite a bit of information about your parameters already, you can get really good results. But it is also very susceptible to noise. So you do have, it's very susceptible to noise, and it's very susceptible to the fact that differential equations, by and large, are highly, highly nonlinear things. So basically, these programmatic methods work better the closer to a linear function you are. In differential equations, I mean, their solutions are mostly analytic functions with no closed form. And so it's just possible that all kinds of terrible stuff can happen. But if you do things carefully and correctly, you can actually get pretty good and reasonable results. Okay, any questions? All right, so I will upload this, and if you want to use any of this fitting methodology, I would highly recommend that you play around with it. It's you know, you may not have, depending on the problem that you're working with or your data set, you may not have the kinds of problems that we're seeing here. And maybe just like that first fit on the SIR model that we did up here, where we just wrote down our equation, ran it, and it fit beautifully. But the things to always check are to make sure that the parameters make sense in your model domain, and to make sure that to make sure that the parameters make sense in the model domain, and to make sure that you don't get any of these little things you don't expect, right? Even if your parameters make sense, sometimes, you know, if you kind of have some idea of what these solutions are supposed to look like, an eagle-eyed viewer can see that something's going wrong. It can be helpful to extend it beyond your model domain and make sure that things are still working. But this is the farther you get in your career, the more you will run across people making shocking numbers of people making these kinds of mistakes. So, okay. So, are there any other questions about fitting and gradient descent and Python and what we have done up until now? Okay. So in that case, we are going to jump onto the second topic, and I'm going to introduce partial differential equations. I'm going to introduce partial differential equations with the grandmother of all partial differential equations, the heat equation. Okay. So one of the things that actually we're going to want to use partial differential equations for, we're going to see that we can use them for next week. We're going to start with heat because that's the, you know, that is the first, that's sort of the partial differential equation. But it turns out that you can use partial differential equations for all kinds of models of population movement and things of that form. It's actually kind of why we took the diversion through heat flow. And because, you know, yeah, so we'll see next week one quick application to predator-prey models, There's definitely something to be worked out for the SIR model in PDEs. I'll show you how to construct it. I haven't seen a huge amount done with it at this point, but I can show you how to construct it anyway. And then we'll finish off with agent-based models, which it turns out have another kind of interesting or a connection between a sort of agent-based viewpoint and partial differential equations. Okay, so what's the idea? Let's recall our heat through the wall setup. So our heat through a wall setup was that we had our wall, had some area, we have some section, delta X, and we have heat flowing through. We have roughly the rate of heat change in the section is given by the rate of heat being conducted in minus the rate of heat being conducted out. Okay, so before, at thermal equilibrium, we always set this to 0. But let's move away from thermal equilibrium. Let's actually allow the heat to change in time. So we can allow heat to accumulate somewhere or diffuse out. So let's move away from thermal equilibrium. So let Q, as before, it's going to be the specific heat times the mass times the rate of change of the temperature. Then we have the following. So then heat flow is Cm times partial U partial T is equal to J of xt. So now, of course, everything is going to have a time dependence as well, time dependency and space dependence. So the heat flux at time t in position x is going to be the heat flux. So this is heat in, heat out. So we can now define the wall density. So this is going to be, let rho be the wall density. So that the mass is equal to rho times area times delta x. Really, we're just trying to get a delta x back in there, right? Before, we could just divide by delta x because we had a 0 on the left-hand side. We need a delta x back in there, but that's okay, right? The mass of this section is going to be proportional to delta x. So then we're going to have C times the density times the area times delta x du dt is equal to J of xta minus J of x plus delta x times t. Dividing both sides by a delta x, we get C rho partial u partial t is equal to minus j of x plus delta x, sorry, there's an a here, t minus j of x t over delta x. So taking the limit, we have C, specific heat times the density times du dt is minus dj dx, which is just k times d squared u times dx squared. So we can simplify this by combining constants. And we have our first partial differential equation. And it's partial differential equation because it's in terms of the partial derivatives. And this is, like I said, this is sort of the grandmother of PDEs. This is the matron of 19th century classical physics and classical mathematical physics. This is everything that we know in classical mathematical physics in some sense comes from this equation. It's not true, but it's very close. But I mean, it's shockingly close to being true. And so this is what's known as the heat equation. All right. So how do we solve a PDE like this? Actually, does anyone know off the top of their head? I'm sure that some of you have seen the heat equation before. So the way that we solve the heat equation is, well, we sort of go back to our tactics from before. We're just going to try separation of variables. There's a lot to be said about solving the heat equation. I don't want to, this is, but a first crack is to use separation of variables. So the idea here is to assume we can write this as just the product of two functions. Assume that we can write u of x t, not as a function where x and t possibly mix, but in terms of just two one-variable functions, phi of x and g of t. So these are nice single variable functions. So then, what does that mean? So plugging in, we're going to have, so du dt is just going to be equal to phi of x times g prime of t. Great. And this is supposed to be equal to d squared u dx. Well, that's just going to be the second derivative of phi times g of t. And so then what we can do is we can rewrite this by just pulling all of the x's over to one side and all of the g's over to the other side, right? So let's just rewrite this. So we have, what's my alpha to actually be on the correct side? 1 over g of t dg dt is supposed to be equal to alpha times 1 over phi of x d squared phi dx squared. Okay. So how can this be possible? The issue here, of course, is that we've got a function of t on the left-hand side, and we've got a function of x on the right-hand side. So equal. And the solution is that we can assume that they're both constant, right? So in fact, a function, I mean, when I say how, I mean, so a function of x, the only way a function of x can equal a function of t is if both functions are constant, right? Otherwise, you could move x without moving t and the equality breaks. So both must be constant. Okay. And this is going to allow us to solve them. So what do we have? So we can solve lambda equals, I'll call this 1. Lambda equals 1 over g times dg dt. Alpha over phi d squared phi dx squared. Okay. And now we're actually comfortably back in the world of one-dimensional problems. So for equation 1, how do we solve this? Well, what is the solution to equation 1? We are back. We keep returning cyclically to the first day of class, and we're back here again. What do we think? Lambda is constant, and we've got 1 over g dt. How do we solve that? Exactly. So integrating both sides. Lambda dt equals 1 over g dg, or g is going to be equal to some a, c, something like that, doesn't matter, e to the lambda t. Exactly. For 2, well, okay, this is a little bit more difficult, but we can just use our theory of higher order differential equations, right? So we're just going to rewrite this as what? Alpha phi double prime minus lambda phi equals 0. So the characteristic polynomial is alpha r squared minus lambda equals 0. This is a nice homogeneous thing. So r equals plus or minus the square root of lambda over alpha. I am going to, sorry, I'm going to make my life a little bit easier here by just doing, sorry, I'm going to make an adjustment and just pull the alpha over to here, because then the alpha is just going to wind up here and I don't have to worry about it here. Right. Sorry. Okay. So we've got that. And we have our solution. Phi is equal to C1 times e to the lambda x plus C2 e to the minus root lambda x. Great. And that's it. So we can then write our whole solution. So u of tx is equal to, well, we can, of course, we can multiply this a by the C1 and C2, but it's just going to be up to some overall constant. So C1 e to the root lambda x plus C2 e to the minus root lambda x times e to lambda t. Okay. All right. Any questions so far? Okay, so here's the secret. Sorry. Any questions so far? I'm gonna wait more than 3 seconds to start talking again. For 1, should be integral alpha lambda dt. That is absolutely correct. Thank you. Any other questions? Okay, so here's the thing about PDEs. In the world of PDEs, the boundary conditions. So the heat equation is a first great example. But what you'll find in the world of PDEs is the boundary conditions really are the entire game. The boundary conditions determine everything. This was true before. We actually already started to see with the heat equation. If you remember at the end of the last lesson on heat, when we were deriving all that thermal resistance stuff, that was, we were starting with a very, very simple equation. And then basically, I mean, a linear equation. The boundary conditions were giving us all kinds of interesting sort of non-trivial results. For PDEs, the game is even more so. We'll see next week that oftentimes you can't even solve the PDEs, but the boundary conditions allow you to kind of integrate things out in a way that I shouldn't say where you can completely solve them, just not in the way of writing down a closed form equation. And I just want to see a first example of that. So this is a kind of classic heat example called the homogeneous boundary conditions. So the heat equation with homogeneous boundary conditions. Out of curiosity, again, how many of you have seen the heat equation before and done some of this this solving the world of PDEs? Yeah, that's it is something that can again be easy to miss unless you wind up in like a thermo background with some calculus. So some calculus teachers and classes will cover it. A good differential equations class will, but it is one of the most sort of important industries in mathematics, but it can actually be fairly easy to sort of miss it. So it's good to get a flavor of this anyway, because it comes up all the time. I mean, if you want to be, yeah, it comes up all the time for various reasons. But basically, yeah, I can only speak to my world. In my world, it comes up all the time because it turns out that you can define topological invariance of spaces in terms of this. But okay, so assume that we have homogeneous boundary conditions. So this is assume that functions, sorry, assume u of 0t equals u of lt equals 0. So that means the temperature is 0 at some along, some strip. Okay, so then what are we going to get? So this seems like a completely reasonable thing to assume, right? If we have defined our heat equations, 0, of course, this is not Kelvin. This is, this could be any base point in 0, so Celsius or something. It's completely reasonable to assume that we've got some function that has boundary conditions that are the same for all time. All right, we're just holding them there. Okay, so then what is this going to tell us? So then basically that means that we must have that phi of x, so then we must have phi of 0 equals 0, which is also equal to phi of L. right? If that's true, then this whole thing's 0 and we're good. And so plugging that in, we're going to have 0 equals C1 plus C2. Which is great. This implies that C1 is equal to minus C2. And 0 equals C1 e to the root lambda L plus C2 e to the root lambda, so minus root lambda times L. Let's just put in that first condition. Okay. And that's a bit of a problem, right? So we can, so for instance, another way to put this would be C1 is 1 minus e to the minus 2 root lambda L. So I've just pulled out the C1 and then I've just multiplied through by, so I've just divided through by e to the root lambda L. So we need to have 1 equals e to the minus 2 lambda L, which is not possible. It's not immediately possible. Greater than 0. Okay. So certainly if L is equal to 0, then we're fine, or if lambda is equal to 0, then we're fine. But if lambda is equal to 0, then we're in a trivial case. And if L is equal to 0, then we're in another trivial case. So this is like a bit of a problem, right? Because like this seems to, we've come up with a completely physical sounding situation, right? Where we have just the same temperature on both sides of a wall. And we follow through our Fourier's law logic. And we seem to wind up in a case where the only possible conclusion is that the entire wall is a constant temperature for all time, right? Or the entire metal bar or the entire medium. So that seems incorrect. And so how can we get out of this? There's a standard mathematical trick to try to get out of this kind of thing. And what's it going to be? We've used it before. What should we do whenever we see an exponential function not working the way we want it to? Yes. So Euler's formula, of course, is as long as we continue assuming this is real, is not going to be very useful. But that logic of saying, let's just complexify lambda and see what happens. What if we complexify lambda? It's less than 0. Then exactly. So then we're trying to solve the following. Then we need 1 equal to, sorry, my brain's fried, cosine of 2, sorry, I'm just going to make, so root absolute value of lambda times L minus I sine 2 root absolute value of lambda times L. Okay, so this holds. Exactly when the absolute value of lambda is, so, well, we need sine to be equal to 0 because this thing had better not be imaginary, right? Or sorry, it better not be complex because this is a real valued function, and the right-hand side has to equal 1. So this is going to hold exactly when 2 pi, oops, no, sorry, we've got a 2 already. Pi times n over L squared. For n and z. So we actually have a discrete number of solutions. Before, when we looked up here, it looked like we basically had this whole continuous family of solutions depending on lambda, right? Here, sorry, depending on lambda C1 and C2. So we have this sort of huge family of solutions, and now we discover that we don't, right? If we want to impose the homogeneous boundary conditions, then we're suddenly locked down to having an infinite but discrete number of solutions. Infinite but discrete number of solutions. And these are given by, sorry, u of tx is cosine two pi n over L, sorry, times x times e to the, correct, what is e? E to the lambda. E to the pi n over L squared t. Oh, times minus alpha. Okay. All right, any questions? And so let me change this constant to a just because I don't like the c cosine. So this is quite interesting. So what we see here is that we have this whole family of solutions that look like, so for n equals 0, for instance, we have, if we look in the domain, so if this is our u and this is our x and this is our t, what do these guys look like? So the n equals 1 solution is roughly, so if this is L, and this is 0, it's going to do a full sort of cosine arc, right? And then what happens as we move forward in time? Well, it's going to diminish, right? It's going to basically keep the same form, but it's going to be multiplied by a decreasing exponential. Until it becomes asymptotically flat. where this line is roughly e to the minus alpha. So this gives us a whole bunch of different possible initial configurations just based on the boundary condition that we're holding the two end temperatures fixed. All right, any questions? Okay, so that is your basic introduction to PDEs. The homework is, so again, the homework is just going to be a bonus. It's just going to be a couple of little problems around PDEs. I would say if you're going to focus on one thing, focus on the project, and I would like to set up times to explicitly meet with people about that. So I'll be holding my normal office hours, and I would encourage you to come and discuss things with me during my office hours, but also I'd encourage you to set up an appointment with me, and I'll be sending out an email trying to actually solidify some time to do that. But the homework, basically, it's going to be a little bit of preparation for next week, but it's fairly straightforward. So what it goes through is Brownian motion and random walks. And so how do you, so let's say if you want to simulate some kind of random motion, like random particles in heat or random, molecules in the air sort of bumping against each other. And what you'll see here, and we'll do a mathematical version of this in class, is that you can actually, in a very, very solid way, you can show that the Brownian motion actually directly gives you the equation. So that if we assume that what's actually going on is that we have little particles and they're vibrating against each other and they're knocking against each other and they're moving around a little bit, that the dynamics that we get out of that are exactly the dynamics of this heat equation that we just derived. We'll talk a little bit more about that next week, because that difference is sort of one of the deep reasons this winds up getting used in population dynamics as well. But okay, are there any questions before I send you off into a weekend?
Professor, for the previous example, could you please change to the notes?
Yeah, sorry.
Sorry. Yeah, for the not this one, but the previous one. Yeah. Yes. The answer there should be like e to the alpha lambda t.
Yes, you're absolutely correct. Thank you.
Thank you.
Yeah. Any other questions? All right, well, have yourselves a fabulous afternoon or morning or evening, and I will hopefully talk to everyone or communicate with everybody before next Monday, but if not, I will see you guys then. All right, take care.